Thanks. Yes, another one from Bulldog. In recent years, significant strides has been made in single aerosol particle trapping technology, which made it possible for us now to study individual aerosol particles trapped in air using advanced laser spectroscopy techniques such as laser-induced fluorescence, Raman spectroscopy, cavity resonance spectroscopy. We call this new aerosol technology single aerosol particle spectroscopy. So I'm going to talk about a little bit. Zing is my student. He's working on this aerosol project. Brandon, Steve, Youngler from Army Research Lab, my collaborator. My current research effort in aerosol is supported by this Aero grant, directed by Gordon and Sanko. Single aerosol particle spectroscopy is a combination of single aerosol particle handling and a spectral technique. So here I'm mainly talking about a single aerosol particle trapped in air by Raman and cavity resonance, because single aerosol particle LF has been covered partially in the previous talk, in Youngler's talk. So first, I'm going to give a brief update on the most recent development in single aerosol particle trapping technologies in the air, and followed by single aerosol particle Raman and cavity resonance spectroscopy. And I will leave the discussions for advantages and challenges questions for single aerosol particle spectroscopy later. I want to make a clear claim here. Some results presented here are from the literature because this is relatively update review. Some results are from our recent research efforts done in Army Research Lab and Mississippi State University collaboratively. If we talk about single aerosol particle trapping, we are thinking about two ways. One, electrodynamic trap, we call it EDB, and that was demonstrated early 1950s. And for optic trap, it's based on two types of optical forces, a radiation pressure force and the photophoretic force. The particle levitation for non-absorbing particle levitation was first demonstrated by Ashton in 1970s. Later on, his postdoc used this technology in laser atomic cooling and won the Nobel Prize in 1997, as we know. For absorbing particle, single aerosol particle levitation was first demonstrated in 1982 and based on photophoretic force. We are interested in aerosol, airborne aerosols, biological aerosols, bioaerosols. So mostly in that case, optic trapping is mainly based on photophoretic force, which has two components. One, F delta T, due to temperature difference on the surface of the trapped particle, front and back different temperatures, and follow the direction of laser beam propagation, either forward and backward, because of pushing and the pulling force. The other one is F delta R, due to the difference in surface accommodation coefficients, even the same surface temperature, but there are also this component. In many cases, for light-absorbing irregular shaped aerosol particles, these two components coexist in the photophoretic force. In general, radiation pressure force and the photophoretic force are very small. We are talking about 10 to the minus 11, 10 to the minus 15 newtons. So if we look this light-absorbing carbon particle as example, photophoretic force can be 10,000 to 100,000 times larger than radiation pressure force in many cases for light-absorbing particles. If we are thinking about particle trapped in air, we also consider gravitational force and the drag force, even free convective force, all to be considered to balance the particle in the air. A recent development in optical trap for absorbing particles can be grouped into three categories based on optical trapping configurations or optical trapping schemes. First group, within the last 10 years, people are using many different sophisticated, expensive optic components to build traps, such as hollow beams, Barker beams, optical rings, digitally generated opticators, and specters. In that cases, where particles are trapped in the dark field of the light, which can be easily understood. Second group, within the last couple of years, and people have achieved single particle trapping in air using single focused Gaussian beam. And simply focused Gaussian beam and trap particle. In this case, particles are trapped in the bright field of the light which has not been completely understood to date. And most recently, a single optic trapping device can trap not only absorbing but also non-absorbing particles. This was published early this year, already mentioned in the previous talk by Wang. Okay. Here are a few cases, just quick show examples. This is a two counter-propagating hollow beam trapping scheme. One particle, two particles, multi-particles can be trapped in this device. Even optical cone can be formed by trapped particles here. And by introducing this special designed aerosol sample introduction nozzle, as mentioned in the previous talk, and we show the movie, and we have achieved continuously sampling, trapping, measuring, and releasing of single aerosol particle in air. And we call this actively controlled sampling and trapping, rather than spread millions of particles in air and one particle is caught. This is called actively controlled trapping device. Here is a movie. Here. Yes. I want to show you this after. Okay. Anyway, okay, skip it. But I can describe this. Basically, this is the optical cone, vertex to vertex we have observed, and we call it the movie. But so far, we cannot explain well, and it's not been published yet. I want to challenge all of you, and if you have good answers, we'll be very helpful. And these two cones, they are rotating in counterclockwise directions. And this, if we block the beam, it's gone, and open the beam, and it will be formed again. So we call it counter-propagating optical cones. Sorry about this. Okay, now change from sophisticated two beams configuration to one well-formed hollow beams, and this new device can trap more than 14 different types of airborne and bioaerosol particles, and as shown in the previous talk. And this is in the different wavelengths from deeper UV to near to the visible. And the further modification of this device, as I mentioned in the previous talk, in single optic trapping device for the first time can trap both absorbing and non-absorbing particles in a single device. And this was published very recently. Now we switch from sophisticated, well-shaped, specially shaped trapping beam to single, simply focused Gaussian beam. In 2012, one group for the first time reported single particle trapping using one single beam simply focused. In that time, they claimed cannot be safely trapped particle. Second year, and which was 2 years ago, in the group in South Carolina, they developed a trapping laser power feedback device to use the jittering position of the trapped particle as a feedback and locked the laser trapped particle position by changing laser power. However, in last year, we achieved steady trap the carbon black particle in air using simple singly focused Gaussian beam at this wavelength. Not only trap the particle, we also can walk the particle rigidly, as we can show here. This is set up very simple, and the CW480 laser beam passing through a couple of lens and direct by this mirror and directly focus through this lens to the trapping sphere here. The single particle is trapped in the air rigidly. We can also, hope this is working. Oh, unfortunately, what's going on? Okay, this I really want to share with you. I need technical support. Yeah, okay, okay. I really like to share with you the movies because this, okay, thank you. Because of this newly developed novel optic trapping technology, so now we can think about single aerosol particle spectroscopy. And here I'll briefly mention the most recent work about optic trap Raman spectroscopy and the newest optic trap Raman spectroscopy. I'm talking about optic trap particle. Raman rather than put a single individual particle in the substrate. That's conventional one. And now trapped by electrodynamic balance trap. We talk about optic trap. So first Raman spectra of single absorbing particle trapped in air. Raman spectroscopy was reported in 2012. This is the trapping device used counter-propagating beam. This is Raman spectra of single carbon black particles trapped in air at a different experimental conditions as Raman shifts. We in 2004, last year, use the same trapping device. We have obtained Raman spectrum of the trapped particle in air. This is the Raman spectra of two individually trapped Bermuda grass in air. They have very identical Raman structure here, but for two different individual particles. This Raman spectra of 5 different bioaerosol particles trapped in air. This is oak pollen, this is ragweed pollen, and ryegrass pollen, and Bermuda grass. They have similar Raman structure, but different details. This is first Raman spectra of single pollen fungal spores trapped in air. We have a question here. You may see very weak Raman signal on the very strong fluorescence signature background. That's the challenge for the single particle Raman for the future. This was first Raman spectra of non-absorbing single particle trapped in air. This was done by a group at University of Cambridge, published last year. Their particles are metal oxide solids trapped based on radiation pressure force. So to the best of our knowledge, that's the most recent development in single aerosol particle Raman spectroscopy. Very limited literature available here. Now, single aerosol particle optic trap kept rain down. Kept rain down is a mature, highly sensitive absorption spectral technique from early stage limited to molecular constant measurement in research lab to very recent commercialization in many different application area. This is the rain-down spectrometer. We call the multi-species rain-down spectrometer, developed in my lab and in 2007, and being used by development energy for carbon H213, carbon dioxide, and methane simultaneous detection. So this just shows rain-down spectra is a mature technology. In terms of a single aerosol particle Raman, it comes from 3 different development stages. In the early stage, stage 1 kept rain down for particle ensembles, and the second stage kept rain down for single particle individually falling through the rain down beam but not trapped, and finally kept rain down for single aerosol particle trapped in air. And these are the first 4 publications for rain down for aerosol ensemble. And this one, first publication for single aerosol particle individually falling through the rain-down beam was in 2007 by the Andrew Wang group in the Bristol University. The same group, they report first kept the rain-down spectra of single aerosol particle trapped in air in 2013, followed by 2 separate publications last year and 1 year this year. If we look at technology development from early stages by D.B. Atkinson, they put the millions of particles in the gas seal, measure the total extinction. To nowadays, right now, we have rain-down extinction spectrometer deployed on site to measure the total extinction of aerosol particles. For single aerosol particle individually falling through the rain-down beam, we can measure extinction, scattering, absorption, and the single aerosol albedo, and the refractive index, and both real part, imaginary part, and also look at the relative humidity effect on the single aerosol particle refractive index. This has been done. And also wavelength-dependent extinction. This is pretty much done by the Seoul group at Bristol University, AJ Open group. And this one, single aerosol albedo, is by a group in the US 2008. So now for single aerosol particle trap kept rain-down spectroscopy, we have only 3 publications available to date. And these are coming from the Seoul single group from UK. This is the demonstrated setup published in 2013. They used 1 CW rain-down beam at 532 and 1 part for particle trapping based on radiation pressure because they are particles non-absorbing spheric inorganic particles, and 1 part for the rain-down measurement at single wavelength. Second year, they used 2 beams, 1 CW beam at 532 for particle trapping, and 4 or 5 CW beam for rain-down measurement. They have done a lot of work in terms of refractive index, relative humidity effect, also change size, and also extinction. They started sodium chloride droplets, and all of them are hygroscopic, inorganic aerosol droplets. The sphere, they compared experimental measurements with mean-series simulation, used cavity standing wave mode. And this one is ammonium sulfide, and this is sodium nitrate. Our optical trap cavity rain-down efforts focus on different types. First, we change from hygroscopic non-absorbing sphere inorganic droplets of the size of 2 micrometers in diameter to absorbing irregular large carbon nanoparticles up to 50 micrometers in diameter trapped in air. So this is experimental setup. We got this in the last couple of months. And the second, we use different trapping schemes. Here, we use pulsed 405 laser beam and split 2, and simply focus by 2 lenses to trap the particle in this trapping cell. Here, we call our system is the simplest optical trapping scheme, the most cost-effective. We don't manipulate the beam; it's not necessary. We demonstrate, we not published yet. For rain-down beam, we use ND-arc pumped dye laser frequency doubling and tripling and covering from deep UV to 700 nanometers for future wavelength-dependent measurement. And we demonstrate for, initially by trapping single-wall, multi-wall carbon nanotube particles on the size of 30 to 55 micrometers in diameter. And this one shows the detail of this trapping cell with 2 windows for laser beam pass through and the particle introduction from the top. We have digital imaging and look at the particles motions and trap the particles here. Very brief. Again, unfortunately, this movie not showing. So this is what we have proposed in the proposal a couple years ago, and this is what we have now. First, this one shows the trapped particle stability, and this indicated by the position viewed by the image system, and this by rain-down time. Okay, stop. Then next, this one shows when trapped particle is inside, outside the rain-down beam. We have different extinction, and in terms of this one, reproducible. And this one shows, for this case, we trap the particle first, and then walk this particle through the rain-down beam, step by step, with a step of 25.4 micrometer per step. And in different location of the rain-down beam, we have different extinctions here, and walk through the laser beam. In addition to that, we also have this extinction of 2 different individually trapped particles at the single wavelength, the same wavelength 315. And this one shows extinctions of the same trapped particle at 2 different wavelengths. And I think that's pretty much, we have more to do. This advantage of single aerosol particle, I think partially mentioned in the previous 2 talks, and I would leave this one for our discussion. And the one part coming from single aerosol particle itself, because it's a fundamental unit of aerosol particle, interaction-free with other particles, carry individual chemical composition, and allow us to investigate statute of the properties. And also, we can look at the temporal evolution, both physical and chemical properties change over the time. Another part coming from the advantage of laser spectroscopy itself. It has high spatial and time resolution. Single rain-down measurement can be done within a second. Even we have frequency of kilohertz measurement. And also high chemical sensitivity because based on spectral fingerprints. And also, most importantly, we can look all of these properties change over time by tracking the particle up to many hours. And the challenge questions, in addition to 4 questions I have related to understanding of trapping, forced motions, and trapping different type of particles and devices, and also huge fluorescence background for Raman, and also how can we do simulation and the calculation for light absorbing large particle with irregular shape. In addition to that, from instrument point of view, single aerosol fluorescence has been done, and as we can see from the previous talk, single particle Raman spectrometer is being developed based on my knowledge, and I believe optical cavity rain-down spectrometer will be available too in the future. And finally, I think we should discuss transfer enabling technology development to fundamental aerosol study as well as future application and instrumentation. Thank you very much. Apologize for the